Hmm. I think EMFT sir has extended, isn't it? Hello.
Yes, sir.
Uh,
Sir,
yes. Yeah. What are the things, 6 questions we have completed so far? What are the things we have completed? Anybody can tell? What are the?
Starting torque,
Yeah.
running torque,
First
and
one
maximum.
we have completed expression for starting torque. What is that expression for starting torque? TST is equals to K1. Okay, E2 square R2 divided by R2 square plus X2 square. This is the first question. We have proved it. Okay. Second one, condition for maximum starting torque. What is that condition for maximum torque? R2 is equals to X2. This is the second derivation. Condition for maximum torque under starting condition. Third derivation. What was the third derivation? Running torque. Expression for running torque. That is K1 S E2 square R2 divided by R2 square plus Sx2 whole square. So this is the third derivation what we did, isn't it? So fourth one.
Yes,
What
sir.
is the fourth one? Condition for maximum torque under running condition. That is R2 is equals to Sx2. This was the fourth derivation. And fifth one, what was the fifth one? It is a ratio of full load torque to the maximum torque. Ratio of full load torque to the maximum torque. What is that relation? 2A SF divided by A square plus SF square. What is SF? It is a slip corresponding to full load. SF is the slip corresponding to full load, and A is it is a ratio of R2 by X2. Rotor resistance to the standstill reactance. Yeah. And sixth one, the ratio of starting torque to the maximum torque. Starting torque to the maximum torque. That is 2A divided by 1 plus A square. 2A divided by 1 plus A square. So we did these 6 questions are completed in last 3-4 classes. Okay. And we left with one more theory part of this chapter, that is torque slip characteristic, which is the most important, as I told you. Torque slip characteristics that we have to complete today's class. Torque slip characteristics. It plays very important role as an induction motor is concerned. Okay. So any doubts in these derivations? Okay, just to go through material. Today I'm posting the total material of this chapter. Just today only. Once you go through entire thing, okay, and if possible today I'll start 1 or 2 problems. So okay, next class also problems on all these things. Now coming to the torque slip characteristics of three-phase induction motor. Okay, so here if you draw the torque slip characteristics of three-phase induction motor, it looks like this. It is the torque slip characteristics graph, that you can say. Okay, this part what you call it as a operating region. Okay, this hatched portion is there. Torques here torque slip character. That means torque versus slip. Slip starts from 0 and it is like this: 0.2, 0.4, 0.6, 0.8. What is the maximum value of slip is equals to 1. 100%. The slip, the maximum value of slip is 1, and minimum it start from 0 only. This is the torque slip characteristic plot here. Okay. Now, and this is what you call it as a maximum possible reason at the top of it. Maximum possible reason. So here, if I draw torque slip characteristics, you can see it starts from here. It is a straight line up to here. It goes like and reaches the maximum value, and then it starts decreasing like this. This is for one value. Next, if you increase the load, and you will get one more plot of graph like this. This is the another load. Like this, we can draw a family of curves for different values of load on the. Okay. This is the what you, and this is what you call it as a maximum torque. Once the motor achieves the maximum torque, any further increase in the load on it, the torque will decrease. See, torque is very important. If the motor is not having torque, it will not run the load. We cannot put load on it. Okay, that's why torque should be there. Torque means what? Turning effect. The torque, without torque, it will not take load, isn't it? So this is the safe operating reason. Okay, what is a practical value of slip we can apply is that is 2 to 5%. The practical value of slip can be 2 to 5%. 2 to 5%, if you think of 0.02 to 0.05. So that means within less than zero point 0.2 only we have to operate. Less than 0.2 only we have to operate. 2 to 5% means what? 2% means 0.02. 5% means, so for example, if ns is equal to 1500 rpm, so what is the 5% of this? 5% of this is 75 rpm. So 1500 minus 75, so we can run the motor in the range of 1425 rpm only. We can apply the load when the rotor speed is 1425. It is better to operate in this range only. If the rated speed is 1500, you can apply the load. What happens if you apply the load? What happens to the speed when you put the load? ಏನಾಗುತ್ತೆ speed is increasing or decreasing when you put load? What happens to the speed of motor if you increase the load on the motor?
Decrease.
Decreases. Obviously, no. When you put, if one person is moving in a vehicle, if three persons are moving in a vehicle, what happens? The speed will decrease, isn't it? Similar way here also, if you put load on the motor, its speed decreases. So what is the speed allowed to decrease? Hardly 100 rpm. We should not go beyond. That is operating. The standard practical limit is 5%. They can decrease the rotor speed. They can apply the load. They can go up to 5% only maximum. It's not fair. If you go on increasing, it will, the maximum torque will reach, and then any further increase in that, it will decrease. Torque will decrease. When torque decreases, what happens? Motor stops. It will not run. So that's why the safe operating reason is what we have shown the shaded portion here. The safe operating reason is up to 0.2%, isn't it? 0.2 value. 0.2 means this is what we can write. 20% almost. 20% is a maximum allowed. But here, but actually, strictly speaking, within this range only, we have to operate the induction motor. So how we got these plots? So we know the starting torque, and you know that running torque formula. What is the running torque formula? We have T is equal to K is there, no doubt. K S E2 square R2, right? R2 square plus Sx2 whole square. This is the running torque. Because to study these all this characteristic, we use running torque only. Fine. If you see, when the slip is equal to 0, what is the torque value from this equation? If slip equal to 0, if I substitute here slip equal to 0, what is the value of torque? Torque is also 0. When I substitute slip equal to 0, torque is also 0. Hence, the curve starts from 0. The curve is starting from torque slip characteristic curve starts from 0. Because when the slip is 0, torque is also 0. Next, when the motor starts operating, its speed will increase, and it is running at, let us say, more than 1400 rpm. Okay, normal operating range 1440, 1460, 1480. Let us, it is operating normally. When it is operating under normal operating condition, here R2, what happens here is, under normal operating condition, the term Sx2 is very small. The term Sx2 is very small compared to R2 value. Compared to R2 value, Sx2 is very small. So that means this term we have to neglect. Already K is constant, E2 is constant. Therefore, torque equal to, what you can write, remaining terms are K is constant, take out. E2 also will not consider. What is remaining here? R2 divided by, this is neglected. When the motor is operating at rated value, at full load condition, normal operating condition, Sx2 is negligible compared to R2 value. Therefore, this term is neglected. What is remaining then? R2 square. Therefore, R2 cancels. So what is remaining here? Torque is equal to slip divided by R2. As you know that R2 R2 is only is considered here. Slip is almost negligible in this case. So what happens here? The torque is from this equation. What you can get? Torque is directly proportional to slip. For fixed values of R2, torque is directly proportional to slip. Okay, R2 is also constant. Okay, for fixed value, this is the R, this is a 2R, this is the 4R, something like 6R. The value of R is fixed for different values of rotor resistance. So we can have plots, different plots. Here, what you have to understand here is the torque is directly proportional to the slip. When the motor is operating under normal condition, the torque is directly proportional to the slip under normal operating condition. That's why you get a straight line here. This you observe. Up to maximum torque, all the graphs are straight line. This is the reason where torque is directly proportional to the slip. Torque directly proportional to the slip under normal operating condition. Under normal operating condition, the torque is directly proportional to the slip. How we got this one? From this relation. K is constant, E2 is constant. This is neglected compared to R2. So what is remaining? Yes, R2 by R2 square. R2 cancels. One more R2. So from this equation, so torque is directly proportional to the slip for a fixed value of R2. The T is directly proportional to slip. That gives the torque slip characteristic is a straight line characteristic up to maximum torque. Then what happens if you still, once it attains the maximum torque, this is called as when you get the maximum torque under running condition. What is the condition? When R2 is equal to Sx2. When R2 is equal to Sx2, these conditions are reached. Maximum torque is attained by the motor. After that, if you still further try to increase the load, what happens? You see. What happens to the slip value when you increase the load? Ns minus N divided by Ns. Okay, now Ns is standard value, 1500, let us say. Now 1440, now the load is now divided by Ns, 1500. You calculate and tell me what is the value of this slip. 1500 minus 1440 by 1500. How much this value? Tell me. Is it 4% or 3%? Hello? Can you able to hear me?
0.4%.
Yeah, 0.04. It will be in percentage, isn't it?
4, sir.
0.04 or 4%. Now, I'm still increasing the load now. This is same. Now, when I increase the load, what happens to the speed? Now, let us say the speed comes to 1200 divided by 1500. Now, it calculates the slip. When you put more load, speed will decrease. Rotor speed will decrease.
2%, sir.
How much?
2, sir.
Check it. How much it is?
0.2, sir.
20%.
20%. 0.2. It is 0.04, 0.2 it is. So what is happening? What you are observing here? As you are increasing the load, that means you are increasing the slip. You're increasing the slip. You're increasing the load on this. That means, see here, the load is increasing. As you're increasing the load, the slip also increasing like this. But slip can be only a smaller value. We cannot increase beyond 0.2. 0.2 is a 20% already. It is once it reaches the maximum value, if you increase still further loading on, slip will increase. When the slip increases, so what happens here is, after that, after the Tmax, after the maximum torque, here R2 is negligible. R2 is negligible compared to Sx2. R2 is negligible. In the first phase, Sx2 is negligible. For a normal operating condition, when the motor is operating at normal condition, Sx2 is neglected. R2 is considered. But as you're increasing the load, R2 becomes negligible. Sx2 is considered. Now in the same torque equation, K S E2 square R2 by R2 square plus Sx2 square whole square. Okay, this is the formula. In this we have to, this k is constant, e2 constant, limit of r2 is neglected here. So what happens is s divided by s square x2 square it becomes. That means s cancels. So what is remaining is torque is proportional to 1 by s. Torque proportional to 1 by s. That means when you increase the load, okay, in the first phase, what happens when the slip increases? When the torque slip increases, torque also increases. In the beginning phase, normal working condition, torque is directly proportional to slip. So we got the straight line characteristic. After the maximum torque, any further increase in the slip. So what is happening? You can see it. Torque is decreasing. Okay. Any further increase in the slip value, torque will decrease because it is inversely proportional to the torque. Here it is directly proportional to the torque. Slip is directly proportional to the torque. But here you can see. After the Tmax is reached, after the maximum torque is reached, any further increase in the slip, torque decreases. If you increase the slip, as you can see here, 4% to 20%, you increase the slip value. When the slip increases, torque decreases. That's why after the maximum torque, so what you observe here is decrease in the torque. This is the torque value. So if you increase the slip value, the torque is decreasing. Torque is decreasing. Okay, but in the here you can observe the torque is directly proportional to the slip for a normal operating condition. 1400, 1440, 1460, that is a normal operating speed. If you increase the speed, it will attain a maximum torque, and further still if you go on loading on it, what happens? Slowly motor speed down, that the torque decreases, and finally it becomes stop. Motor stops. Eventually motor stops. There is a limit for the operation. The safe operating reason is the shaded one, which I can see here. 0 to 0.2. This is the safe operating reason, normal operating reason of induction motor. If any further increase in this, you can achieve maximum. But any further, the motor torque decreases. When torque decreases, if you put still load, motor stops. That's all. It will not run as a motor. Motor stops. Torque becomes 0 means. Okay. So this is what the torque slip characteristics of motor only it is. But this, the beauty of the induction motor is three-phase induction motor. So here it can be operated in three different modes. It can be operated in three different modes. As a motor, as induction motor, we can operate. We can run as a generator, and you can run as a braking reason also. We can apply the braking mode, generating mode, motor mode, braking mode. It can be operated in three different modes. So that is a very interesting characteristic of this induction motor, three-phase induction motor, that you can observe this diagram. This is what indicated. Just observe this. Torque slip characteristics of three-phase induction motor with three different operating reasons. Can you able to see all of you?
Yes, sir.
Yes, sir.
Hello? Can you able to see?
Yes, sir.
So far I explained only this graph here, only from here to here, 0 to 1 slip value. Slip is 0, here slip is 1. Isn't it? So see, motor can be operated in the motor operating reason, generating reason, and braking reason. We can operate the induction motor in three different modes. This I explained already, isn't it? As the slip increases up here, it is a straight line, it reaches the maximum, and any further increase in the slip, the torque decreases. Torque decreases. And it stops here. It can stop. At 1, slip is 1. When standstill condition, we call it as. See, we can apply the brake also to the induction motor. We can apply the brake to the induction motor. How it is done? How to stop the motor? How to stop the motor? Let us say it's a very interesting thing. 1 minute. See, we know that the induction motor is running, rotating magnetic field is running in this direction, let us say. This is the direction of rotating magnetic field. I explained already. When three-phase supply is given to the RYB, we are giving RYB, three-phase supply is given to the stator winding. The rotating magnetic field is running like this in the clockwise direction. Rotor is also rotating in the same direction. The rotor is also rotating in the same direction. Now, if you want to operate the induction motor in the braking region, what we have to do is you interchange these two terminals, any two terminal. Okay, interchange any two terminals. We have this is the terminal box of this. Okay, like this. These are the motor terminals, isn't it? R, Y, B, and these are the supply terminals. They are supply terminals and motor terminals. Just what you do is instead of connecting to R, now connect to R to Y and connect Y to B and B to R. Just interchange the terminals, any two terminals of the supply. What happens, you know? The rotating magnetic field changes its direction. It clockwise it is rotating, isn't it? Now it will rotate anti-clockwise. But rotor don't know. It is still it is running in the clockwise direction. But immediately when you reverse the terminals, that what is happening here is there is a opposite torque is exerted here. Opposite torque is exerted. We are applying the brake to the rotor. That means it stops immediately. The rotor stops because rotor is running with the help of normal, that is a this what clockwise rotation. But immediately if you reverse these terminals, the rotating magnetic field changes its direction. That means it is opposing the normal rotation of the rotor, and this process, what you call it as a plugging. This phenomena is called as plugging. Okay, this we practically apply this also in order to stop the induction motor suddenly. This is one of the approach. Reversing any two terminals of the stator, motor suddenly stops. So that reason, what you call it as a, this is the stop reason. Okay, this reason when slip is greater than 1. All these three operations depends on slip value only. Slip between 0 to 1. The value of slip between 0 to 1, it acts as a motor. It acts as a induction motor. If you increase slip value greater than 1, it acts as a braking reason. And that how it operates in the braking reason, just now I explained. Just reverse the any two terminal, interchange any two terminals. The torque, rotating magnetic field changes its direction opposite to the normal direction of rotor. That means we're applying the brake. And one more interesting thing, when the slip is less than 0, when the slip value is less than 0. Less than 0 means what? Negative slip. Negative slip. How we get that negative slip here? We know that slip is equal to ns minus n divided by ns. When you get the negative slip, see, normal working of induction motor is what? Always induction motor runs less than synchronous speed. If synchronous speed is 1500 rpm, the n value, motor speed will be 1490, something like that. If the synchronous speed is 1000, motor runs at 970 rpm, something like that. But when you have this, when rotor speed is more than the stator rotating magnetic field, if you run the motor above the ns, that means now I am running, this is 1500 minus 1600 rpm or 1800 rpm. So what you get here, the value of slip becomes negative. Negative value of slip you get, isn't it? Because this is greater than this means what? You get the negative value of slip. We are running the rotor by some extra mechanism above ns value.